So, let us see the sum limits. Okay. The first one very simple is, if suppose an is a sequence which is n to the power p, a sequence of real number, where p is a positive or negative rational numbers. Then limit of this sequence an as n tends to infinity will be, if p is positive, the limit will come out to be plus infinity, is it not? That is because as n increases, it unbounded sequence, and so it is plus infinity. When p is negative, then the limit will come out to be 0, it will tends to 0. Okay. So, when p is this and less than 0, we are getting them, and when p is 0, then the limit will come out to be 1. So, it is simple, that it is nothing to prove, just then another sequence, suppose an is x to the power p, where x is any real number. X is any real number, x to the power n. So, let it be n. Okay. X to the power n, clear? That is an's x to the power n given. Now, this n will go to plus infinity if x is greater than 1, because x is greater than 1, each term of the sequence is greater than 1, and in fact, it keeps on increasing. So, increases to infinity. So, then and when it x lying between minus 1 and plus 1, it means mod of x is strictly less than 1, that is mod of x is strictly less than 1, absolute value of this is less than 1, then in that case this sequence will keep on decreasing and decreases to 0, and when x is equal to 1, the limit is tending to 1. What happened to that when x is strictly less than minus 1? When x is strictly less than minus 1, or when x is equal to 1, minus 1. When x is equal to minus 1, it is basically of the form minus 1 to the power n. So, this is an oscillatory finite series, oscillatory finite, because the limit will it will go to plus 1 minus 1 like this. So, mod of this thing is bounded, but if an x is strictly less than minus 2, then it is a oscillatory infinite, is it not? It will go oscillatory infinite, plus infinity minus infinity it will go. So, we get this. Okay. Then third limits, if an be suppose x to the power 1 by n, where x is positive, Now, when x is positive and n is any integer, then what happens that when x is greater than 1, each term of the sequence is greater than 1. So, when x is greater than 1, the terms of the sequence sequences, that is 1 x, x to the power half, x to the power 1/3 and so on. These are satisfying this point, x is greater than this, x to the power half is greater than this, is greater than this, and all the terms are greater than 1. It means it is a monotonic decreasing sequence bounded below, is it not? So, it is a monotonic decreasing, strictly decreasing sequence which is bounded below, monotonic decreasing sequence bounded below. So, it must have some limit, because every bounded sequence is limit. So, it will have the limit, it will have some limit, say L, and this limit, therefore, L will be either greater than or equal to 1. L will be either greater than 1 or equal to 1. Suppose L is strictly greater than 1. Suppose we say, okay, then what happens this? That is x to the power 1 by n, limit of this x to the power 1 by n, this limit as n tends to infinity tends to L, which is greater than 1. So, that is only possible when x to the power 1 by n should be strictly greater than 1 for all n. Okay. Now, this shows that x must be greater than L to the power n, is it not? Limit x to the, and this is true for all x. But when L is greater than 1, then this is not true for all x. This should be true for all x, which gives a contradiction. Why contradiction? Because for given x, one can find n naught such that x will be strictly less than L to the power n for n greater than n naught, because this keeps on increasing. Right hand side is keeps on increasing, but the left hand side is fixed. Once you choose the x, left hand side is fixed. And what we are saying, that if limit of this is suppose L, which is strictly greater than 1, it means for large values of n, or when x, what is the behavior of x? X will be exceeding L to the power n, is it not? It will be greater than L to, then it will goes on decreasing and decreases, say something like that. But here is leads to a contradiction. Once you fix up the x, and since L is greater than 1, so when n is sufficiently large, this will keep on increasing. So, a number n naught can be obtained, so that x can be made as it can be made less than the term L to the power 1 after a certain stage. And its contradiction is because of a wrong assumption that L is greater than 1. Therefore, L must be equal to 1. Is this clear? So, what we conclude is that limit of this, therefore, limit of x to the power 1 by n when n is sufficiently large is 1 when x is greater than 1, for x greater than 1. Okay. And for x equal to 1 already true, for x equal to 1 also it is true. So, let us now, if x is strictly less than 1, is it not, then x we are choosing positive. Remember, this is x is a positive. So, we cannot choose the minus or something, x is positive greater than 0. So, if 0 less than x less than this, then what happens to this? L limit is there, is it not? So, we can get a contradiction here again, because x is less than 1, and we are choosing the limit L, because if x is less than 1, what is the behavior of this sequence? Yeah, if x is less than 1, the terms of this sequence will be what? It keeps on increasing. This keeps on increasing, is it not? So, then x is less than x raised to the power half, less than x to the power, and so on, if x is less than 1. Okay? X is less than 1. So, what happen is increasing function of this. Okay? And then what when x is equal to 1, but it is always be less than 1 and less than 1. So, when you take the limit of this x raised to the power 1 by n is suppose capital L, which is less than or equal to 1. But again contradiction, if L is strictly less than 1, we get a contradiction in a similar way. Therefore, L must be 1. So, what we conclude is that limit of this, therefore, limit of x to the power 1 by n when n is tends to 1 is always 1 for x greater than 0. X negative is not defined. So, that is why we are not choosing, because x negative the roots are not reals. So, we cannot get it. So, this is one. Now, if we take this is our fourth problem, limits. Suppose we take a n's to be n raised to the power 1 by n. Now, we claim that limit of this sequence is we claim that limit of this a n as n tends to infinity is 1. As n is sufficiently large, this basically tends to like this. Okay? So, how to justify limit to be 1? So, first what we will show that this sequence is a monotonic sequence. Okay? If we prove it is a monotonic decreasing or increasing, okay, if increasing bounded above, if it is decreasing then it is bounded below, then it limit will exist. So, first is we claim this further the sequence n to the power 1 by n is a monotone decreasing sequence, is a monotone decreasing sequence. Monotone decreasing sequence. Why? This is our claim, because suppose it is true, then n plus 1 to the power 1 by n, because suppose it is true, suppose it hold, then it means that is this is should be less than n to the power 1 by n. As n increases, it decreases. So, we claim that this is a decreasing sequence, monotone decreasing.
Sir,
n plus 1, n plus 1 exactly. So, we are getting this. So, what we get is n plus 1 to the power n is less than n to the power n plus 1. Okay. Now, this is equal to, when you divide by n, then we get 1 plus 1 by n to the power n is less than n, is less than n. Now, this is true, this is true for n greater than or equal to 3. As n is sufficiently large, for n is equal to 1 and 2 it will not be true, but when n is greater than or equal to 3 it holds. The reason is because 1 plus 1 by n to the power n, apply the binomial expansion. So, 1 plus n x plus n minus 1 over factorial 2 and plus n minus 1 n minus 2 over factorial 3 like this. So, suppose I apply the factorial, then what will be this say last term up to n term, then we get 1 by n to the power n. Clear? Just like 1 plus n x plus n n minus 1 and so on, okay, just binomial. Okay. Now, this will be equal to what? 1 plus 1 plus 1 by n square will also come, n n minus 1 factor 2 into x square. So, 1 by x square, this is 1 by n cube and so on. So, n gets cancelled, we get 1 minus 1 by n by factorial 2, then 1 by factorial 3, 1 minus n minus 1, 1 minus 1 by n, 1 minus 2 by n, and like this up to so on. Okay. Now, you see this each term is positive, each term is positive. So, the sequence 1 plus 1 by n to the power n is a monotonic increasing sequence. Of reals, because when n increases, the terms increases here. So, and this is positive, this is positive. So, you are adding some positive terms here again. So, it is a monotonic increasing sequence. Further, this sequence for all n, this at least greater than 2, because these are positive things. Okay. But this sequence further 1 plus 1 by n to the power n is strictly less than 1 plus 1 plus 1 by factorial 2, 1 by factorial 3 plus 1 by factorial n. Is it not? That will be, and this is last term n to the, okay, clear? That will be factorial n. So, this one. Now, this will be further less than or this is further less than 1 plus 1 plus 1 by 2, 1 by 3, 1 by 4 and so on, 1 by 2 square, 1 by 2 cube and so on like this. So, it is 1 by 2 to the power n minus 1, 1 by 2 to the power n minus 1, because factorial 2 is equal to 2 basically. Okay. So, so first term is additive, factorial 3 is greater than 2 square. So, 1 by factorial 3 is less than 2 square, 1 by factorial 4 is less than 1 by 2 cube, 1 by factorial n less than 2 to the power n minus 1. Now, this is a geometric series. So, what is the sum of this geometric series? Is 3 less than a over 1 minus, so it is less than 3. Okay. Is it okay? 1. So, this it means this is a monotonic increasing sequence of real number which is dominated by 3, bounded by 3. So, it must be a convergent sequence, and limit of this cannot exceed by 3 and will always be strictly greater than 2, at the most it may be 3. So, limit of this n, so limit of this, so sequence 1 plus 1 by n to the power n will have limit lying between 2 and 3. Okay. And in fact, we denote its limit by E, and it was shown later, it will be shown that limit of this as n tends to infinity 1 plus 1 by n to the power 1 E, where E lies between 2 and 3, and it is irrational number 2.7 something like that. So, this will be the limit. Now, here we are discussing about this part. We are, it is given the n to the power 1, we are interested in finding the limit of this. Now, what we claim, this sequence is a monotonic decreasing sequence, which is already proved. When n is sufficiently large, greater, this is a monotonic decreasing sequence. Monotonic, but each term of this sequence is greater than 1, or equal to 1, because n is 1. So, it is a monotonic decreasing sequence is it not, and each term is greater than or equal to 1. So, now, so since n to the power 1 by n is a monotonic decreasing it is a monotonic, this sequence is monotonic in decreasing, is it not? Decreasing sequence, which is bounded below by 1, is it not? Because n to the power 1 by n is greater than equal to 1, at least for when n is equal to 1 you get 1, okay? N is 1, you get 1, 2 it is greater than 1, is it not? So, it is monotonic decreasing sequence. After 3 it is there, is it not, n to the power 1 by n, because this is 2 for n is greater than equal to 3. So, after 3 this is decreasing sequence, but all the terms will definitely greater than 1. Did you get me or not? But you cannot say when n is equal to 1 and 2, you cannot say that n is equal to 1, but rather than n equal to 2 it is greater than 1, when n equal to 3 onward it decreases. For n is equal to 1 and 2 it increases, clear, but when n is 3 onward it decreases. So, it is just like this, it goes like this and then decreases, okay. So, this is 1, this is 1, and here is something 2 to the power under root, and then it keeps on decreasing and decreases to basically again 1, like this, okay. So, this is a, therefore, the limit of this sequence a n, when you say limit of n exists and we get the limit to be 1, limit of n to the power 1 by n when n tends to is L, okay, we get limit. Now, this limit is greater than or equal to 1, is it okay? Now, we claim L cannot be greater than 1. Now, if L is greater than 1, then again we lead a contradiction, then we get a contradiction. Why? Because n is greater than L to the power n, L is greater than 1, so not possible, not possible for n greater than equal to 3, okay. 3 cannot be greater than some number power 3, okay. So, that will be more. Suppose L is equal to 2, then what happens? 3 cannot be greater than 2 to the power 3. So, it is contrary. Therefore, L must be 1. So, limit of this n to the power 1 by n over n is 1, okay. That is also interesting limit. Then, okay.